got it. Right. All right, let's get started. We have 46 participants. Hello, everyone. Welcome to the topology optimization webinar. Just a couple of words before we start. Well, this is a restart since April last year. And we have been discussing with colleagues and also with students about how we can organize it better so we can attract many students and also faculty members. And we decided to keep the frequency, so we will still run every month. And the duration is reduced from 1.5 hours to 1 hour. And regarding the format, we will have, we want to make it more accessible to young researchers in this field. So we will start from education or review article with about 20 minutes, followed by 2 latest paper on the same topic. So every session will be resolved around a particular topic. And today we are very happy to have Joe Alexandersen from the University of Southern Denmark organizing a session on fluid topology optimization. Joey, thanks, and please take it from here.
Thank you. So welcome everyone to this webinar where the theme is, as June said, fluid topology optimization or topology optimization of fluid flow. So last year I published a sort of educational article on how to do density-based topology optimization, or one way to do it. There is no only way to do it. So this is my way of doing it. I'll go briefly through that. So the paper is called a detailed introduction, but today we do not have time for the fully detailed, so it'll be a brief introduction. Then afterwards we have Maarten Theulings to give a presentation of his paper, which focuses on an interesting aspect of fluid topology optimization, is the sort of the accuracy of this immersed forcing term that we add to do this kind of thing. And then after that we have Elie, who will show some large-scale level set-based topology optimization with anisotropic mesh adaptation. So one of these slightly different ways of doing topology optimization than the first two here. So first, it's me. So I'll give a brief introduction, as said. So first of all, I don't know the level of people here, so I thought start at the bottom. So structural optimization is the optimization of structures. I bet you hadn't guessed that. But a structure is sort of classically defined as an assemblage of materials which is intended to sustain loads. But structural optimization, that term is also used more broadly for structures that are not necessarily intended to sustain loads, but perform some kind of function, be it fluid mechanics, heat transfer, acoustic, and so on. And then the optimization is sort of the act of making things better, right? So we have 3 types of structural optimization. Won't go into details here, but we'll be focusing on topology optimization or generalized shape topology optimization, which is where we have a stronger design freedom. We're able to change the connectivity of the structure or the topology by adding or removing holes. And some methods have the benefit that we are basically able to start from no predefined design and have something appear. In all topology optimization, but in particular also in fluid topology optimization, we have some different design parameterization cases. So what we're used to doing in sort of classical engineering would be to sort of have this explicit boundary. We have our geometry, that's what we mesh. We mesh the fluid channels and we simulate the fluid inside those channels. We can also do optimization on that, and that has certain benefits, but also some drawbacks. Then we have the material distribution approach, or the ersatz material approach, or density-based approach. It has many different names, but that's where we have a more weak representation of our solid, which has, again, certain benefits, but also some drawbacks. And then we can go to immersed methods, which is sort of a combination of the two, you could say, but in order to sort of capture this this boundary, we do some advanced integration and possibly also enrichment. So the bookkeeping for this one can be a bit more heavy, and that's, I think, why material distribution or density-based approaches are quite common and quite easy to implement. So that's what I'll focus on today. This is just to show one example, and it's mostly to show that this structural optimization, topology optimization, is an iterative approach. So every frame in this animation down here, that is 2 simulations, one to say how good is my current configuration, and then one to give us the gradients through the adjoint method. And potentially more simulations if you have multiple load cases or multiple functionals you want the derivatives of. But that means that simulation cost is quite important when we're doing optimization. That's where the work that Elie has done and will show makes a lot of sense. So topology optimization originated in structural mechanics. In fluid dynamics, it's much younger. So it's from 2003. So coming up to just over 20 years now. So a lot has happened and a lot is happening. It's a very active field, especially when we start adding other physics on top of the fluids. You can see more in our review paper. But in contrast to the structural problem, where the problem is sort of where to put the holes and how to place material, the material distribution problem becomes where to put the channels and how to place the obstacles. So same question, phrased slightly differently. So as mentioned, this lecture or this short presentation is based on this recent tutorial paper, educational paper, which comes with a MATLAB code similar to as we're used to within the structural mechanics world. It is available on GitHub, and there's also a preprint there, which is more or less complete. So you can just read the preprint if you don't have access to the final paper. So there are many ingredients. These are common for all topology optimization, but in the context of fluid mechanics, they fill a little bit more than we're used to seeing for solid mechanics. So 88 lines is not a lot when you're doing this kind of thing. But the paper goes through all of these steps, or at least attempts to describe these steps, and then the code is sort of built in a similar way. So the way what we want to represent is this discrete representation of a fluid channel with some embedded solids. Ideal cases, these are fully separated, well-defined, and a clear interface. But then what we do for topology optimization using the density-based approach is we introduce a characteristic function which we relax. So instead of being 0 or 1, it is somewhere between 0 and 1. And this allows us to use gradient-based optimization methods, which have proven very, very powerful in this context. But a drawback is that we get this implicitly defined solid-fluid interface. It's no longer a well-defined line. It's sort of defined by this contour of this design field. And that has certain drawbacks when you go to high-speed flows, or at least it can if you don't do something smart. So the starting point is the steady-state Navier-Stokes incompressible here. And as we are used to, this should only live in the fluid. There's no flow in the solid, so these equations are not active in the fluid. But in order to do topology optimization, where we're changing the distribution of solid and fluid organically within the same design domain, we need to relax that. So we do that by adding a body force or resistance term or a momentum sink into the system, where essentially we add at the place of this force some large number multiplied by the velocities. So if we're in the solid and we set this to infinity, this term will dominate and we will get ui should be equal to 0. So that's what we want in the solid, and then we want to recover the original Navier-Stokes equations in the fluid by setting this to 0. Now, we're not living in this discrete world, we're living in this continuous material distribution world. So we kind of have to couple this alpha not only to the values of 0 and 1, So are we in the fluid? Are we in the solid? It should be coupled to this field that can vary between 0 and 1. So how do we do that? How to define this function? That's a good question. We have to first look at the bounds. So before I had 0 and infinity, now we say that when we're in the fluid domain, it should have a minimum value. When we're in the solid domain, it should have a maximum value. For sort of numerical reasons, we cannot use infinity, so we have to use some finite upper bound, which is large enough, but not too large. What does that mean? Maarten will also talk a little bit about that. And then the bottom, if we're doing 2D simulations where we have a finite out-of-plane thickness with no-slip walls on those surfaces, then we have to have a lower bound to sort of account for the out-of-plane viscous resistance. And then we have to interpolate, because as mentioned, they are not just ones and zeros. They can be anything between 0 and 1. And there you can use many functions. I use a ramp function where this Q alpha parameter sort of defines the shape of this interpolation curve. That's a whole thing in itself, and I'll skip that a little bit, but you can read more in the paper. So you can look at this, what we call this, the common terminology is Brinkman penalty, but as I was made aware of recently, it's not really a Brinkman equation when we have this. Actually, if this is large enough, it kind of becomes a Darcy equation, so maybe it would be more appropriate to call it Darcy penalty, but nonetheless, people call it a Brinkman penalty. And you can see this as purely algorithmic way to drive the velocities to 0. It's just a big number times velocities. They should be small. And I used to sort of use that point of view for a long time. But particularly for the minimum value, if you're in 2D, as mentioned, you have to couple it to the out-of-plane thickness. And that's exactly what the original papers in this field did. They used this shallow channel approximation to define this resistance term. And then we can also use a porous media analogy where we define it as a function of the viscosity and some kind of permeability of some porous media. The physical sort of bounds have a benefit that they sort of give similar behavior for a range of problems, where if you just choose this algorithmic parameter, the order of magnitude of the alpha parameter has to change when you change your problem. That's a little bit automatically taken into account by these sort of dimensional variations here. This I will skip. It's just to show you need a large alpha to have a small error in your fluid solution, but you can read more in the paper about that again. Now we want to optimize something, so the sort of canonical optimization problem in fluid topology optimization is to minimize the dissipated energy with a constraint on the fluid volume. So the dissipated energy here is a viscous term, and then the energy loss in this sort of porous media, you could call it. Now, then we need the sensitivities or the gradients in order to do gradient-based optimization. So we use the adjoint method. And for the adjoint method, we need 4 partial derivatives. And in my code, these are computed symbolically using the MATLAB symbolic toolbox. So all the hard work is done automatically. And that's by defining the objective functional and any constraints using the MATLAB symbolic toolbox. Just some summations over the indices, and then you can ask it to differentiate with respect to the various parameters that you might need. So it's a nonlinear problem when we have Navier-Stokes equations, so we have to solve it using a nonlinear solver. I use a damped Newton solver. There again, we need the Jacobian. And if we're lazy and don't want to do that by hand, we can just ask MATLAB to do it again. So we define the residual again by summing up over various indices of the weak form. And then I can just ask MATLAB to differentiate. And then I can export it to vectorized MATLAB functions, meaning that I can build the residual vectors and the Jacobian matrices for all elements at once using vectorization. So that makes a relatively fast code, but a very memory intensive code because you're building all elements at once. Now, there are two sort of default problems introduced in the code, and these come from these original two papers. We have the double pipe problem, where we have two inlets on the left, two on the right. We want to find the solution that minimizes the dissipated energy. The pipe bend is an inlet over here on the left and an outlet on the bottom. For the double pipe problem, you can do various variations. If we're looking at Stokes flow and we look at sort of this elongated domain, we see that it's actually more beneficial to collapse two channels that you might be expecting to one, because we're reducing the number of boundary layers essentially, thereby minimizing the viscous dissipation. But then if you change it and add inertia, for instance, you get some other solutions and so on. But again, I don't have time to discuss all the results. If we look at the pipe bend, this is a good example for seeing sort of the impact of inertia. As we increase the Reynolds number, we'll see that this optimal channel that is basically just straight from inlet to outlet for Stokes flow becomes to be more curved and sort of accommodating that the flow is entering with inertia. And then instead of just meeting a wall, we're sort of slowly bending it around to the outlet. There are given a series of extensions, or you could say exercises in the paper. So the first one is sort of introducing passive elements, which is quite normal. We're used to doing that in solid mechanics as well. So here the necessary code updates are given. Then how to implement the MMA optimizer, which we need for more complicated problems. And then the theory is given for the flow reversal problem, which is the mechanism problem of fluid topology optimization. And then lastly, just some very brief theory is giving on a minimum drag and maximum lift problem, where this is then left as an exercise for the reader to sort of implement. So the flow reversal problem looks like this. Very briefly, we essentially have a channel. The flow is coming in from the left, and then we're saying rather arbitrarily, we want the velocity at this point in the middle to move in the other direction. How should my flow channel look? And there I want to limit the pressure drop to be some amount of times larger than the empty channel, because if I just let it do whatever, it can make a very good solution that reverses the flow, but will use a lot of pressure drop to do so. So these are two solutions we see for Stokes flow. So this is for allowing a relatively large pressure drop. This is allowing a smaller pressure drop. And here we see that the solution is just to reverse the flow in the middle by making this sort of S curve here. And what it's doing is it's sort of concentrating the flow also to increase the magnitude and then changing the direction by having this S. If we don't allow as big a pressure drop, it makes this bypass channel, which basically sends most of the flow through here, not impeding it, not causing pressure drop, and then a little bit around here to cross this reverse part. If we add Navier-Stokes, again, inertia plays a huge role in the designs here. And there we see for even allowing a very big pressure drop, we still have this bypass channel, because now the inertia is causing additional energy loss when we're sort of changing the direction of it. So we need this bypass channel even for higher pressure drops. We can also do drag and lift. This is using the formulation introduced by Kondo et al. Back in 2012. We can do minimize drag and then maximize drag with a restriction on, maximize lift with a constraint on the drag. So these are some results for the increasing Reynolds number from top to bottom, and we see we get these more elongated aerofoil-like shapes. And then if we take these same designs and say, maximize the lift, but keep the drag under control, don't increase the drag too much, we get these designs for the same sort of types of problems. And that was basically it for me. I tried to keep it short and brief here. As mentioned, the paper is published in SMO, so you can go pick it up there. If you don't have access, the preprint is on GitHub, and the MATLAB code is in both the paper and at GitHub. Now, I think we have time for a few questions, but let's see if there are any here. Can I see? There are no questions. If you have any questions, you can just put put your hand up or unmute yourself. Otherwise, I suggest you write them in the chat, and then we can come back to them later if some questions pop up in your mind during the next few presentations. Okay.
I have a question.
Yes.
So what do you mean by, you have mentioned design iteration in table 9, in the caption of table 9?
That's a good question. Table 9. In the paper, you mean?
Yeah.
Okay, yeah. So it's because it's if I get this animation here, so it's because it's an iterative process. So we're doing iterative changes to our design. Oh, we see an animation down here, right? So essentially, we start up with some starting configuration. Why is it not running? Oh, here we go. And then we're doing a simulation, updating it, doing new simulations, updating it. So the number of design iterations is the number of designs we have been through. So the number of iterative refinements of this design we have done.
Right. Okay. Okay, thanks.
All right. Then I suggest, oh, there are some in the question here. Maybe I take this. Normalization is not strictly required, but it's always a good idea, especially if you have many different functionals that you kind of need to put into the same algorithm. So MMA has some preferred scales of these different things. So it's always good to normalize things so you don't have things of the order of magnitude 10 to the 8th and some 10 to the minus 8th. Then you can run into issues. And the next question is, can you do it in 3D? Yes, you absolutely can. There's lots of work on that. Oh, now it's pouring in. So maybe I try to answer these while we go on to the next presentation. I can answer them in the track or in the chat. So Maarten, if you go ahead and share your screen.
Yes, thank you. So you should be seeing my screen right now.
Yes, but yeah, try to put in full.
Yeah.
Oh, so yeah, we're seeing the presenter mode. Perfect. Yes.
Yeah, thank you for a nice presentation. So I will continue to show some of my work that nicely follows it, that I did in at the Netherlands Aerospace Center in collaboration with the University in Delft. So we just saw your model with the penalization, but you already introduced that this sometimes has some problem, and it's mainly in how to select this penalization, how to select that maximum value you just talked about. So then we can make two mistakes. We can select it too low. And then if you have here a problem with a thin solid wall, you can get a lot of flow going through such a porous solid wall. Or we can select it too high, and that may cause us to end up in an ill-performing local optima, where we have many leftover features from the iterative optimization process. So that's what I was looking into, and then I also found that big review paper, and there are two questions there that I found interesting and that I wanted to look at, and that was that I wanted to improve the precision of the solution entered optimality. So precision, not too much flow going through the solid domain, and optimality, no convergence to these ill-performing local optima. And I wanted to find some parameter robustness. So what often happens, what I experienced often happened when I did flow optimization, I needed to do a lot of tuning before I found the correct parameter settings. And I tried to solve these problems, or at least improve them, by really looking at the Navier-Stokes equations and how do we actually adapt them for our solid fluid topology optimization. So I want a model that is able to represent a flow domain where we have flow speeds, and a solid domain where the flow speeds tend to 0. And then one of the approaches is to interpret the solid domain as a highly impermeable porous domain. And that opens up a lot of literature in this for porous flow modeling. So what the literature on porous flow modeling does, it looks at that porous domain and defines there a small averaging volume. Here it's enlarged. And in that averaging volume, it can actually look at the discrete solid and fluid phases. And then it uses that averaging domain to construct an averaged field. So this is the averaged field psi, by simply integrating over that domain and dividing by the volume of that domain. So that's the basic tool I use to define a new set of equations that adapts the Navier-Stokes for solid fluid polytonization. And then I can use that volume average here to also define my fluid volume fraction, and that's just the average of 1. So that was also what we previously saw that Joe used, that gamma value. And then finally, I can put the full Navier-Stokes equations through this averaging filter, and then use some maths that's presented in my paper that I won't go through today to find the volume averaged Navier-Stokes equations, the Vance equations. And they have a couple of differences to the equations which we just saw. So first of all, here in the top left, we have an addition of this gamma in the inertial term. And here on the right, we have this completely new term, the second Brinkmann correction. I won't be going into detail into those today because that would be a bit too much. And I want to focus on what I think is the more important term. And that's the pressure penalization. So here we see this gamma in front of this pressure gradient that shows us the pressure forces. So what this does is in the solid domain, this gamma, the fluid volume fraction should tend to 0. And then you're kind of reducing those pressure forces. And in the solid domain, what we often find is that it's basically a balance between pressure forces pushing fluid through and the Darcy penalization at the end, which inhibits the flow. So now we have another option. So normally we could increase this Darcy penalization to reduce the flow, but now we can also decrease this gamma to reduce the flow in the solid domain. And indeed, I call it the Darcy penalization because when I went through all the porous flow literature, there they call it the Darcy penalization. Okay, so we have this new model. How does it compare to the common model? Well, first, we remove the gamma from the inertia term. Then we completely remove that new second Brinkmann correction. We remove the pressure penalization. And then we get the Navier-Stokes with Darcy penalization. So that's what I call the NSDP equations. Okay, I have two models. I need to compare them, but first I need to select my parameters. So I need to select for this pressure penalization a lower bound on the gamma. So in the solid domain, this gamma is at its lower bound of 10 to the power minus r. This will be a value that's positive and smaller than 1. And of course, I need to define my Darcy penalization. So first I define an interpolation function up here on the right. And there's also this alpha overbar. But how do I define this alpha overline? So that's the next step. I need to select my parameters. And I do that by looking at the flow leakage. More specifically, the order of magnitude of the flow leakage, where the flow leakage is the magnitude of the velocities in my solid domain divided by the magnitude of the velocities in my fluid domain. And I want to select my parameters such that my flow leakage becomes predictable. And then I found that this is actually dependent on an elemental Reynolds number, and that compares the viscous and the inertial forces on an element scale. So then it's dependent on h, my element size in my mesh. So that's just the size of one of my square elements. Okay, so then I found that I need to have a different maximum penalization alpha, whether viscosity or inertia is dominant. So when viscosity is dominant, I set it like this, and inertia is dominant like this. And the important thing here to see is that I'm manipulating the magnitude with this 10 to the power of q term. So that's becomes the parameter that I select. the 10 to the power of q, and all the other ones are just mesh parameters or material parameters I define in my problem. And when I define my penalization like that, I found that I could predict this flow reduction for the Vance equations as 10 to the minus q minus 2r, for the NSDP equations 10 to the power minus q minus r. And then I can just select this r. And then we find that for the Vance equations, I have this 10 to the minus 2r, while for the NSDP equation, it's only minus r. And that's because of this introduction of this pressure penalization. So that adds another, adds an increase in flow reduction for the Vance equation. And then of course, this Q I select in my Darcy penalization. Okay, so I have this nice prediction, but of course I need to verify it. So I have a problem with a straight channel with two solid obstacles. And on these obstacles, I measure the flow leakage, UL, which is equivalent to measuring the flow leakage. And then I have these nice results, which I will go to slowly. And I have my predictions. And first I want to check, are they accurate for the Q factor, which is also present on the x-axis here. So then I see for R is 1, I see a nice decreasing slope with -1, which is as expected. And at the end here at Q is 3, with R is 1, then I should expect -3, -2. So a flow reduction of -5, that's what I find. And for the NSDP equations, -3, -1, 10 to the power -4, that's also the flow error that I find. So there, that's confirmed. And then I want to see what happens when I decrease this R parameter. So that's the consecutive lower lines. There I increase R by 1 each line. And then for the NSDP equations, you find very nicely that each increase in R decreases the flow leakage by 10 to the power -1. And for the Vance equation, it's slightly less accurate. So for lower Q, it doesn't exactly decrease it by 10 to the power -2 for each increase in R. But for the higher Q, you see that each increase in R decreases 10 to the power -2. So there, that's a less accurate prediction, but it still results in significant increases if you compare it to the NSDP equations. Okay, now I have this prediction, and now I want to use that prediction to prediction of the flow reduction to select the parameters that are based on two criteria. I want accuracy in my solid domain. So when my design is converged to a solid fluid design, in my solid domain where I'm at the lower bound of my gamma, I want a really low flow reduction of 10 to the power -3. However, I don't want to end up in those ill-performing local optima. And for that, I want to have a bit of flexibility in my intermediate design areas where I have a design variable of approximately 0.5. So there I want to have flow reduction of 10 to the power -1. And here, these intermediate areas, you could also kind of interpret as setting a lower bound with R of 0.3. So then the flow reduction there becomes mainly dominated by the Q that I select. So the magnitude of the Darcy penalization. So then I select for both the Vance and the NSDP equations the Q of 1, but to increase the flow reduction in the solid domain for the NSDP equations, I need a really low lower bound on my volume fluid volume fraction. So there I need Rs2, and for the Vance equations I need Rs1. And then I test that on that problem that we saw earlier, where we have a fluid inlet on the top left and a pressure outlet on the top right. And the goal here is to minimize the pressure at the flow inlet, while the flow has to flow around this thin wall at the center. And then for the Vance equation, we find this nice performing optimum with a nice solid fluid distribution. Well, for the NSDP equations, we find this optimum that has a lot of gray values, and it's an inferior optimum compared to the Vance equation. And those gray values are found because there the penalization is actually already quite high, and that pushes you into a local optimum. So then I tried to find a nice solid fluid optimization by decreasing the penalization, so by decreasing either Q or R. And then I found that then I decreased the Q to 0, so that means a decreased Darcy penalization. I find nice optima for the NSDP equations. So what I basically found was that I need a bit more tuning for the NSDP equations to be able to find an accurate optimum. And that for the NSDP equations, only when I have more flow leakage, so less accurate optimum, do they converge to a good solid fluid optimum. So that brings us to my conclusions. So I first wanted to look at the precision of the solution and the optimality. And I did improve that by adding that pressure penalization that basically only adds flow reduction when you have a converged solid fluid design. And then I wanted to look at the parameter robustness. So that's the second thing I did in the prediction of the flow reduction, and then selecting that parameter, that Darcy penalization. And now I have quite a robust method to always select my penalizations when I do flow optimization. So then I get to my recommendations. So first of all, Joe asked earlier, what should we actually do from your paper? And I think the most easiest thing to do is implement the Darcy penalization. And that's basically just setting a parameter based on your mesh size. And the second thing that you could take away from my paper is that you could try to implement the pressure penalization. In my code, that was only changing one line of code to implement it. So it's an easy try, and I believe it greatly improves the precision of your solution while maintaining a good design convergence. So I hope you will check more of the details in the paper here at the end. And if you have any questions right now, you can also ask them.
Thank you very much.
I have a question.
Yes, go ahead.
Thank you for a very nice presentation, Maarten, and some really nice work. So, as I understand it, this is independent of Reynolds number, or is it dependent of Reynolds number?
The penalization is dependent on the Reynolds number, but on that elemental Reynolds number that I defined. Okay,
good. So it should go, I mean, if you want to go crazy high, it should be no problem.
Yes, but there's one problem, a slide that, yeah, I have it here. I also checked that flow reduction for varying elemental Reynolds numbers. And then I looked at for the low Reynolds numbers, I have that penalization that always works. So when you're sure that your elemental Reynolds number is always smaller than 1, you're fine. But when it's bigger than 1, I tried two things. I tried the standard one, the one for the lower elemental Reynolds numbers, that's the dashed lines and the solid lines. And there I found that it's kind of, with the solid lines, with the penalization that I define, it reduces the flow error still a bit. And that's because I have here this V tilde, and that's an approximation of your flow magnitude. And I overestimate it, so then I get an penalization which is too high, so flow reduction which is lower than I expect.
Okay, good. Thank you very much.
All right, we have time for another question if someone has it.
I have one.
Yes.
So in the second to last slide, there was the optimization results, but it seems to me that there's actually a reverse flow for the Vance equation near the wall on the right side, while for the NDSP, it seems like, at least in the lower right, it seems that it's going upwards, or maybe I cannot really see.
So you mean that here the flow is going upward?
Yeah, or down. Yeah, here it's going downwards, right? Near the wall.
Yeah, downward, and here it's also downward, and here it's going upward.
Yeah,
for these figures, I plotted the flow lines everywhere, just to show that I also have flow in my solid areas. That's not completely gone, but those flow speeds are actually really low. And also here at this kind of artificial channel, that's also has really low flow speeds.
Okay, so we just see, so for the NSDP, we see that there seems to be some sort of source. If I look at the lower right figure, in the same slit, it seems like there's both some flow going up and down, right?
Yeah, and that's because here
What?
I decreased the
there.
penalization by quite a lot. So there's a lot of flow going through this thin wall, and the thin wall is also modeled as an impermeable solid medium, porous medium. And then yeah, you get some weird effects, and that's basically because it's less accurate.
Yeah. Okay, so it really highlights a nice contribution you made.
Yeah.
All right, great. There is one question for you in the chat, but I think we'll do the same. So we'll just continue, and then you can maybe reply that person in the chat. So next up we have Elie. If you go ahead and share your screen.
I'm here. Okay. Share screen. Screen one. Yes, can you all see the screen?
Yes, we see it.
Okay, first, I would like to thank you, Joe, for this invitation. We are really new in topology optimization. However, we are we have long expertise in finite element. We couple that with multi-phase flows and mesh adaptation. So bringing all that to topology optimization, it was nice and cool because this domain is very demanding recently, especially for anything related to thermal management and environment issue. So there are more and more need in this direction. That's why we have interfered. Now, what was the challenge? The challenge was like if we want to go into topology optimization, there is a lot of concern related the computation complexity. If you want to handle something very complex, or manufacturability, that means when you finish with your shape or your form, can we directly take it and print it out, and the precision. So really, the focus of this presentation is about how to solve the equation. Okay, now how we put them in together, I will show all the details. So what we are concerned here is how we evolve the interface in time. We're gonna change it. The topology will change, so we're gonna evolve it. So we need to compute like a certain displacement field or a velocity field that will track this interface. We want that the interface remains sharp, the maximum possible, to high precision, to very high precision. And we need to handle different media. You talked about before about fluid and solid, like using the density approach method. Same, we need to handle different media. It could be even in the fluid itself, it could have like a mixture of fluids. And finally, for a finite element solver, we need to handle high discontinuity ratio for density or viscosity when you are dealing with multi-fluid flow. So if you want to answer all that at the same time, evolution time, sharp interface, handling fluid and solid domain, and high discontinuity, so the solver can iterate well, so you obtain this kind of simulation. So you have the inlet from this side and the outlet from this side. This is very nice example where you have the fingers, and now you let the fingers and you go further away with this Z shape. Just an illustration. We will comment it later. Okay, but you have here the evolution in time. You have the sharp interface. We can handle two zone. Blue is fluid, red is a solid. And there is a high discontinuity because you are solving everything on an Eulerian mesh. So you need that the solver can handle that. Okay. So, and our dream, it's one day when we finish this shape, we can extract we can kill all the rest of the element and keep the shape to print it out. And I will show it in 3D later. So I will show the 4 or 5 ingredients. The first one, a level set, I think that everybody knows about it. I can give you all the details. We level set is a function like 0 and the interface positive inside the surface that you want to handle and negative outside. You can cast it in a transport equation. There is a way also to avoid transporting all the fields, like all the levels, by doing some filtering and change the variable from of the test function. So you can have this kind of function. So what you see here, there is a parallel or with what Joe presented. That means we are going into a two zone with interface, and this interface is controlled by this thickness. And finally, you cast it into an equation that has a nightmare of being a transport equation, convection equation in finite element that you need to stabilize it. And the second nightmare, it's you want to keep it at a distance function the whole time. So either you solve Hamilton-Jacobi equation again, or we have casted out the reinitialization of the function directly into the transport equation. We have popped up additional terms. These terms, rather than being such a source term, they can be as a reaction term, which increases the accuracy of this kind of resolution of the transport equation. Okay. And then when you have that, you can mix the property from one side to another side using the heavy side of this function for the density, for the thermal conductivity later, for any material properties. Okay. The second ingredient is dynamic anisotropic meshing. So the idea is to have, you have these two meshes. If your physics is on a boundary, let's say, so it's smarter to put your 2000 element where you need them. So this is the philosophy, okay? And you are keeping 2000 elements. That means for the same resource power, you can decrease some element where you don't need them and increase where you need them. So you need a metric for that. The metric is like a tensor that have the direction and the amount of mesh adaptation in each direction. And what we used here is we use the natural metric. That means you position yourself on a node, and the metric, it's like, it looks at all the edges that surrounding these nodes, and then we can control the set of these edges by an error, and this error is controlled by the gradient of the solution. So when you have a gradient, you have such element. When you don't have a gradient, you can remove all the meshes. So what I'm telling you here, that the idea is when you finish your form, you can remove these 5, 6, 7, or 10 elements that remaining surrounding the shape, and then print it out. The third ingredient is about how to solve the finite element solver, the solver itself. Even if it's a flow here solver, or even it's gonna be Darcy, you need to take care in finite element how to solve in a P1, for example, resolution, P1 for the velocity, P1 for the pressure. So there is a way of doing it using variational multi-scale approach, which are very nice. The idea is to solve for the large scale that you can handle on your mesh, and for the small scale that bring you stability in the case of Darcy, in the case of high Reynolds flow, is to model this small scale and to replace that effect into the large scale. So you end up with this equation. I want to solve the Navier-Stokes equation plus additional terms that come from the small scale. This gives you the stability that you need. And this is very important. I think all the ingredients together are important. So finally, we end up with this chart that you start from your initial shape, you solve U and P, you solve the adjoint solver, also solve using variation multi-scale approach, and then you compute your sensitivity to control the interface that you give it to the transport equation, and then you move your interface. When you move your interface, you need to follow it with the mesh, and you make conversion. You check that if you are converged. If you are not converged, you do another mesh, another iteration, and then you iterate until the final shape. We check the surface constraint, and then we adapt the mesh, and then there is a lot of some details about normalization, about doing some filters and binary filter to keep the velocity control on the interface and not inside the solid and inside the fluid. So to show you some illustration, this is an example about the pipe, bending pipe. And you can see that at the end, the idea is it smooths out all the elements that you see at the end. These elements here can be killed, so you can keep your surface very smooth as desired. And he will show all the details about the convergence until the number of iteration, until you get, you verify the cost function. And these are examples in 3D. The first one is related to same principle about the 3D bending a pipe. But if you want to go and change the configuration, doing like two different inlet and outlet, you obtain this kind of resolution. And we have pushed this example so far, which is very known, and we kept it iterating. You can see, you can appreciate the smoothness of the surface, and then we kept it iterating, and then it gets finally another shape that we didn't see. We let the computation going along, and it's find out that it can go further into the optimization and get this this form. Okay, and I will show last example. This is with thermal. We have added to the framework thermal boundary condition on this one, on this part. And this is for distribution of the flow, one inlet and different outlet. So again, it's the combination of the 4 ingredients to make it work, okay, with some iterations that can cost maybe on the mesh adaptation part and on the iteration to solve. But since you are doing small deformation every iteration, it works very good and it's stable. And there is 2 papers on that. The first one, all the details it's like to highlight that everything turns in parallel. So the mesh adaptation for each domain decomposition can be handled by the mesher, and then they communicate all together. And there is another one where we have added the thermal. So there is 2 papers with all the details that you need about it.
Thanks a lot. Very nice results here. So do we have some questions from the audience? So I have a quick question. So maybe I didn't hear it. So are you using are you imposing hard boundary conditions on the surface, or are you using a Darcy term similar to
very
what we
good,
did?
very good. It's what we call the immersed method. It actually, to penalize the region of the solid, you can do it different way. You can do it as a Darcy. You can increase the viscosity. If you have a high viscosity in the solid region, it will behave as a solid because you push the rate of deformation towards 0, okay, and it becomes a solid. Okay, and also there is a forcing term. In our case, we use high viscosity with Darcy. Like both can help.
Okay. Okay, that's interesting. Yeah, because I think I remember way back someone tried to do it just by changing the viscosity alone, and that wasn't enough.
Yes.
Maybe Casper is saying yes, so maybe he can chime in here.
And there is another issue, strong one. I find out later when I discuss with people that the fact that we solve U and P in a mixed formulation, it's more important than solving U alone and then P and then correct for the velocity.
Yes.
So we are using a mixed formulation U, P in the same matrix. So for the preconditioning of this matrix, when having a high viscosity in one region and more low in another region, it helps. And behind the linear algebra, we use PETSI for the resolution.
Okay. Yeah.
I don't know, what should I do? I should go into the chat.
Yeah, I can read the 2 questions there. So one is, what is the approximate time it takes to do an optimization in 3D, similar to the examples you showed?
Yes, very good. The question is without saying with how many number of processor, we cannot answer. That mean this is the idea, is if you parallelize everything, okay, that means you can be safe on this question. In the paper, I will show you, we put all the details. I don't know if you start looking at this paper at the screen.
Yes.
For all the test cases in 3D, we give a complete table about the computational power here.
That's good. Yes.
Okay, and then we highlighted who is costing the best, who is the consumer.
Yeah. So now I see the mesh adaptation is the majority here. So is that done in parallel also, or
Yes,
is that
in parallel. The whole idea to say that it's in parallel.
Yeah, great. Next question, does the method presented generalize to different objectives and constraints? Also, is the code public?
Yes. The code is not public. So sorry, I'm saying yes,
Yes.
for it. Yes. The code is not public, but we are willing to collaborate because this is a very old, not very old, like a very old habit in France for every school to have its own code, because we work with industrial, so we wrap everything what we're doing and we give them a software at the end of the day. Okay, but we are happy to collaborate. Okay, now for different objective function, it's doable. We are doing the same benchmark now, just to compare to other research team. Okay, and recently, I'm doing a lot of coupling optimization and topology optimization with AI. So we are pushing forward, and we're happy to have any comment or contribution by email later, so we can compare on other examples. All that is not our finding. It's we went into it because we are new in topology optimization. We went and we saw what are the benchmarks to repeat them using this alternative approach. I will never say it can better than other method. It's only alternative, and this is what Joe you're doing. It's like you are putting all people together to share
Yes.
yeah.
Yeah, I really appreciate you coming here as an outsider, but now you're an insider. So we hope to see you too at the various conferences and so on. Any other questions? Otherwise, I think we've maxed out the time.
I will put my email on because maybe I didn't put it right away in the chat.
Yes. Otherwise, I'm sure we are all findable if you Google our names. But yes, we have the email in the chat here. All right. Thanks, everyone. Does June and Nils want to say something?
We will have our next session on the 27th of February. It will be a topic on design for additive manufacturing or design for manufacturing. It will be organized by my colleagues Matthijs Nangelaar and Chang Ayers. Both are here today. So I also look forward to seeing many of you in February. And Joey, thanks for organizing the session today, and it's nice to see you.
Yeah, thanks a lot. Thanks for the good turnout. Yeah. Right. Great.
Have a nice day. We'll have a nice evening.
Yes.
Yes.
Thanks.
Bye.
Bye, everyone.